Отлично. Okay. So 1 second.
Let's go.
Okay. Welcome back, everybody. So first of all, are you all in our Telegram group? Yes? Great. So if some of you in home is not in our Telegram group, please write in the chat or something, okay? Because that's very important. All the information will be there. That's the yes first. In that group, you found 2 files. The first one is the exercises for class, the problems for class, and the second one are the problems for home. Okay. About the deadline, well, I still don't know the deadline, but you can start with the defense of your problems the next week if you want. Okay. So that's it. But if we have new information, then I will write about that. Okay. So you had your lecture yesterday, right? And what did you study in your lecture? Do you remember what? Predicate, right? So a predicate. Yes. So you defined what a predicate is. So what is a predicate? Do you remember somehow, like anyone? You can write in the chat if you want. I will try to read all the comments. I will try. That's not very easy, but okay. Okay, so a predicate, I would like to call it a property, you know. So let's call this a property. Okay, so why? Because if we have x, then and we have some predicate phi, then if we write phi of x, means that x has this property. So that for x, property phi holds, right? And we can say this is true, or I mean for some values, this can be true or false. Okay. So what is the difference between a predicate and a statement? So if we have this is a predicate, yes. But if we defined some value for x, so for I don't know some x, that some fixed x, then this is the statement. Okay. So we have statements, we have predicates. Good. Next, what else? You should have studied the quantifiers. So these 2 important quantifiers, right? So for all, and there exist. And let me check, what else did you study? So that should be, so in yesterday, yeah, predicate. Yeah, and that's it. I think that's more or less everything you studied yesterday. Well, today we will follow with the exercises. So we finished with exercise number 4, right? Now we begin with exercise number 5. Okay, so number 5. I'm not going to write it down, or do I need? So I think everyone has the problems, right? So, but okay, I'm going just to say the problem. I can write it. So put the following arguments in symbols and check their validity. So whether you get a tautology. So check their validity and put them in symbols. Yeah. So number 8, we have, if he doesn't tell her, she'll never find out. So if he doesn't tell her, she will never find out that. So this, and what else? If she doesn't ask, he won't tell her. He won't tell her. And she did find out. So she must have asked. That's it. So we have many statements here. We have many logical connectives here, and we have. Okay, let's find out. So if he doesn't tell her, she will find out. This is the first statement, right? Then, if she doesn't ask, he won't tell her. This is the second statement. And we have a third statement. She did find out. So she must have asked. Okay. So we have two big statements here. Before and after this. So we have three statements, and how are we connecting them? So let's define first this. So ask. So let's define predicate. Okay, ask, and how many? So what kind of predicates are? So we have unary predicates, binary, and so on, right? So we define this predicate, ask. Do you think how many variables should I put here? 2, right? Because like she asked him, okay? So ask, I don't know, no. How many? Just 1, right? She knows. And tell. And tell, I think, too, also, right? He tells her. He tells her. Okay, so we have these predicates, right? And we have to, we have now to say this using what? So let's begin. If he doesn't tell her, so tell x, y, xy. If he doesn't tell her, then she will never find out. So known right? If he doesn't tell her, she will never find out. Okay? This is the first one. Now we have to write the second one, but what do we need to write here? And, or, if and only if, and. Okay? We are telling, like, we're telling this, and then, so we have a statement, and this, okay? So every time, if we just have a dot here, and there's not any and or something, that's and, okay? If we have or, then it will be written or, okay? So, and what? If she doesn't ask, so if she doesn't ask, then he won't tell her. Tell if she doesn't ask, then he won't tell her. If she yeah, well, it depends on how we define it, but yes, it's much better if x, so if y doesn't ask x, right? You mean that? Yeah, much better that way. And what else? She did find out. So she knows, right? So we have three statements, and we have a big, so this is everything, all this is one statement, and we have the following. So she must have asked. So yeah, and that's it. So it's written in symbols. That's the first task. Now we need to verify if this is a tautology. Again, always you have to do that. Okay, so again, what do we need to do? Okay, so 1 second, please. For those who are online, should we submit the solutions? No, for those online, we should talk in Zoom or Skype or something. Okay. Okay, so what do we need to do? We want to verify that this is always true. Okay, so we need to, yeah, we by contradiction always, do not forget that. So let's assume that this is false. So it means that this is false, right? And all these have to be true, right? And now, if this to be true needs, so we have and here, and. So each of the parts needs to be true. Okay, so this needs to be 1, and this needs to be 1, and this needs to be 1. Okay. So what do we know? We know that she did not ask him. So we know that. Okay, let's write that way. She did not ask him, and we know that she doesn't know. No, that she knows, right? What else? So let's go. So no here. So this is 1. So this has to be 0, right? And this is 1. So this has to be 0. So he tells her, right? Yes. So he tells her she knows, and here, so this is 0 from here, yes, and so this has to be 0 again, right? So she asked and we got the contradiction, okay? So somehow she asked her, but she did not ask. Uh-huh. What? Yes, this. What is true? So true implies true. This is false implies false. This is true. No? Yeah. So false implies false is true. Okay? And that's it. So yes, this is a tautology, but yeah, this is one way, but we could actually like resolve this problem just in words. So what do we know? We know that she did find out, right? She did find out? Yes, we know this. Okay? So let's suppose that she did find out, but she didn't ask him. If she didn't ask him, then he won't tell her. And if he doesn't tell her, then she will never find out. Okay? So we have that she find out, but she will never find out. So we got the contradiction just in words. Okay? Right. So, by the way, the last seminar I made a couple of mistakes. Some students know that, and yeah, I already post that in the Telegram group. Okay, it happens, right? So if I make some mistake, please tell me, because it's really difficult from here to find them out. Okay, so next, B, 5B. So, oh, this is a long one. Okay, unless taxes are raised, there will be a defeat. If there's a defeat, state services will be curtailed. Therefore, if taxes are raised, state services will not be curtailed. Okay, well, let's find it. So unless taxes are raised, there will be a deficit. And if there's a deficit, state services will be state and therefore if taxes are raised, state services will not be okay. That's it. Now, do we have any volunteer? No? Sure? Okay. In the next one, you will have anyway to come here. So we need. So yes, we defined. You defined in the lecture what a predicate is, and when we have a predicate, we have some set. Okay, let's not call it set. A collection of variables, right? So you have a predicate and some x here, and all these x, possible x together. How did you call it? The domain, right? So the domain. How did you write that? The domain of phi. Okay. So this is all. This is like the basic set, or I don't know how to call it, that contains all these x. Okay. And if we want to resolve, for example, this problem, we need to find the domain, okay, of each predicate. It's very important. So let's find it. So let's call that set, I don't know, this some big M. So this M, this is going to be the domain, okay? So we have taxes, what else? We have state services, and that's it. So okay, so we have also deficit, and the deficit state services will be no, and therefore if taxes are raised, service okay. And for each of these variables. What so? Yes. What can we need to define? Let's call it the set of predicates, or I don't know how do you call it in the lecture. But what can happen with each of these values? So what can happen with the texts? They can raise, right? So let's write raise. Yes. If there's a deficit, the state service will be carteled. How do I write that? I really don't. Okay, just that. And if textures are raised, again, state service will, and that's it. Yes. So we have two predicates. Yes. And each of these predicates can take each of these values. Not deficit. Deficit is just can happen or not happen. Okay. But texts can raise or in state services can cartel. Yes. Okay. So let's write this somehow. Unless texts are raised, there will be a deficit. Okay, unless texts are raised, there will be a deficit. So texts, no, raise. What there will be deficit. So deficit. Yes. So what do I need to write here? Unless. If not. Unless text is raised, there will be. Yeah. Yeah, looks like true. Unless text is raised. So if this is true, then there will be a deficit. No, if. Yes. Yeah. Okay. That's it. So this is the first one. Then we have, if there's a deficit, state services will be cartel. So if there's a deficit, then what? And here we write state services, right? Yes. So if there's a deficit, state services will be carteled. Yes. Therefore, so if texts are raised, so if texts are raised, state services will be not cartel. So this won't happen. Right, the service. Yes. Yeah, is it correct? I think it is, but I'm not sure. But I think yes, it is correct. So I'm not sure about this one. Unless this. Okay, let's say it's correct. So again, what do we need to do here? Yeah, so let's check if this is false. Then all this has to be false. And then what do we obtain? What do we have? So if this is false, then this is true. Yes. And then the state services are complete. Okay. Okay. Now, what else? So all these have to be 1. Yes. So this and this, so this and this has to be 1. And but we have that this is false, right? Then if we want this to be 1, then this should be false. So we have that no deficit. And since this is false, so this should be false as well, right? Yes. So and happily we did find a contradiction, so this is a tautology, so this is true. Okay? And that's it. Everything's clear? Yes? What part? Okay, so we have that this is all equals 0, right? So this part has to be 0, and this has to be 1. And if this is 0, it means that this is 1. This is the first thing we wrote, and that this is 0. So that is 1, right? Because we have the negation here, right? So we have these first two values. And now here we have that this is 1, everything is 1 till here. So, and we have end. So we have a statement number 1 and a statement number 2. So this has to be 1, this has to be 1. And since we already know what we know this. We know the value of this. So we can put this value here. And then we know that this is false. And then since this should be 1, then this should be 0. Oh? This can be 1? From false, if so this could be 1. So if we have A, B, 0 and 1, this is 1. Yes. Yes, that's true. So, so what do we need to do here? So let's not think about this one thing. So let's think about this one. Then this is true. Yes. So this is true. And then this is true because we saw that this is, so this is true, and we have no contradiction. Yeah. Or what? So one. This is 1, 0, 1. Well, maybe we don't have a contradiction here, but that's weird. That's weird. I think we do need to find the contradiction. So here 1 and 1. Yeah, we have that, right? No? Because we have that this is 0, so this is 1, for example. And then this is 1, and this is, if this is 0, then this is 1, and everything works for some reason. Well, maybe it's not true. I don't know. Well, we could verify that. Let's leave this to the. So let's verify that later, okay? And that's it. Because you know this is so. Just all these sentences or originally are written in Russian. So in the translation, sometimes it's, I don't know, it gets complicated how to understand the meaning of the words. But okay, I think you understood, and that's very good that you find out that there was a mistake. So next. Now we have, what exercise is that? With the city? No, not with the city. So exercise number 6, we have to review the exercise number 1, and we have to write everything with quantifiers and predicates. But I think we already did that. So that's it, okay? I don't know what in the first exercise we're supposed to do then if we didn't have to use predicates. But okay, so the 6th exercise is already done, okay? Now number 7. Translate the following statements into logical symbolism with a reasonable choice of logical atoms. So the same thing than always. So the first one is, so this is number 7. 7A, okay? Peter is either older than Paul or is wiser than any other man. So again, so we have Peter is either older than Paul or is wiser than any other man. So first of all, let's define the domain, and in this case we have, let's call it all men. Okay. Okay. So all people. Okay. Why? Because we are well, man. Okay. We are talking about than any other men, so we have to talk about all men. Okay, or all people, all men. And what predicates do we need to write here? Older, yes, and wiser, right? Yes. So 2 predicates, older and wiser. And look at the sentence, and you tell me. We have here or, yes, but is this the typical or that we've defined before? So look, Peter is either older either or. So it's or so either this or this, but not both. Okay, so this is not just or. This is a different one. So if we have, for example, if and only if. So if we have here true, then this is true. If we have here false, then this is false, right? So to be true. And but we want the opposite. We want that if this is true, so either this is true or this. So we are going to define some kind of negation of this one. Okay? So we need this, that this is true and this is true. Okay? And how are we going to do that? So how do we write A if and only if B? So this is A implies B and B implies A, right? And all we have to do is the negation of this. Okay? Because every time when we have here true, we're going to get false, and yeah, the same way. So let's write this. We can write it just using this. I mean, this is not correct, but if we write that this, so like this is equivalent to this, then yeah, like we can write it. We already know where this comes from. Okay, and then what do we need to write? Peter is either older than Paul, so older Peter than Paul, right? Or wiser who? Peter. Or wait, so Peter is wiser than X. So X is all people, but do we need to write what? So either Peter is older than Paul, or Peter is wiser than all the other men. So what do we need to add here to say that all the other men? So the X is just one man. So let's write all Peter is wiser than all the possible X. So, right? So for all X in here, so for all the men, all the people, Peter is wiser than them, okay? And that's it. In the case of 0 and 0, what? Okay, look. If we have and if we have here 0 and 0, no, where 0 and 0? So look, we have this, right? And we define the negation of this. So we will obtain the negation, no? Just so if we have A, B, A implies B, A if and only if B, right? So we have 0, 0, 0, 1, 1, 0, 1, 1. So we have 1 in two cases, in this case and in this case, right? And now if we are defining like the negation of this, then we should obtain 0, 1, 1, and 0. Yeah? Okay. And that's it, okay? So next. B. What B says? Each odd natural number is a sum. Number is a sum of 4 square numbers at least one of which is odd. So let's write this. What do we need here? What will be this set? So we are here, we were working with all men, right? And now we are working with what? Numbers, yes. What numbers? Natural numbers. So we take a set of all the natural numbers, right? And great. So let's write that. Each odd number. So how do you write each? For all, yes, yes, for all, yeah. For all n such that for each odd natural number. So for all odd, how do we write odd again? Do you remember? So right? For all odd natural numbers, okay, or each odd natural numbers, what happened? So is a sum of what quantifier do we need to add here? For all these kind of numbers, there exist, right? What? Yeah, so there exists what? So for this number, for example, take a number with this property, and we say that there exists this combination, right, that represents this. But to write this combination, what do we need to write? The existence of what? So we have 4 square numbers. So we have to say that for each of these numbers, there exists A, there exists B, there exists C, and there exists D. So all the 4 numbers such that, so let's write here, such that what? N is equal to A squared. Yes? And what else? And at least one of which is odd. So, and how do we write that? That at least one of these numbers is odd. Yes, or, okay, so and A is odd, or B is odd, or C is odd, or this odd. Yes? We need to add. So, that's it. Is this true or false? There's something called the Lagrange Theorem or something like that. Well, it's proven that for any natural number, any natural number can be expressed as the sum of 4 squares. But we have something a bit different here. So this is an odd number, and then one of these has to be odd. So I think this is true. Okay. So I think this is true. It's proven for 4 squares. For 3 squares or for 3 squares it's not proven, I think, or something like that. Okay. So I think this is true. And next. So is everything clear? Let me. Where? Because this D has to be odd. So it's not even, right? So it's the same in all of them. Yes? D can be divided by 2. Yeah, the last seminar we defined that. Okay. Next, let me check what's the next exercise. Yeah, see. Let me. Okay, we have some questions there. A way to use the table for some with this kind of question. What kind of question? I don't know. Can we write m instead of x? Is it okay to write only one exist? Could we just use another set A1? Yes, of course. You can write any numbers here. So A or A1, B, A2 or something. It doesn't matter. Not to write them all again. I don't know. Okay, I will check your questions a bit later, okay? So, number C. We have, so the following system of inequalities. So we have this system of inequalities, x squared plus alpha y is greater or equal than 2, and alpha x squared plus 2x minus 3y is equal 0. And we say that the following system of inequalities has a solution in real numbers for some positive value of parameter alpha. So alpha is positive, and x and y belong to the real numbers, right? So we need to write that with symbols. How are we going to do that? So first of all, is it clear, right? All the possible values we can take are Well, Masoud Vehit, sorry, I can pronounce your name very good. Maybe you're right. We will have to check that. Okay. So first of all, this, and now we need to write that. So tell me. So let's read that again. The following system of inequalities has a solution in real numbers. So has a solution in real numbers for some positive value of the parameter alpha. So has a solution, So how do we write that this system of inequalities has a solution? Yes, there exists. Great. So there exists x, there exists y, and what else? There exists alpha. Yes. Such that for some positive parameter alpha holds, so that this and this holds, and that's it, right? So x squared plus lambda y is, and alpha x squared plus 2x right here, or minus 3y, yes, equals 0. So yeah, and that's it. Okay, there it is. So this is more mathematical. This is more familiar for us. And don't worry, we will finish with the language. Just talking about language very soon. We will talk about mathematics. I mean the mathematical objects. Okay. But we needed that. Anyway, so in the last one, D, every real solution of the equation. So D, we have the equation x power of 12 plus 44 x power of 7 minus 23x equal to 0. So every real solution of this equation is a root of a certain linear equation with real coefficients. Okay, the solution for all, every solution of this equation is a root of certain linear equation. Okay, let's write that. So first of all, every real solution for all x, right? For all x with what property? That is the solution of this, right? So for all x such that this, such that this holds, right? So there exist A and B and C such that what? Ax squared plus bx plus c is equal to 0. Yes? So this x, for all the x from here, there exists some linear, so for all x from here is the root of some equation of this type, okay? And then we need to write that there exist such coefficients, right? A, B, and C. And what else do we need to add? We need to add also that and A is not 0, right? Because that's the definition of this kind of formula, okay? So that's it. Hmm? I don't have to say that's what? Ah, yeah. Yeah, well, we already wrote that here. So this only can be real. Okay? And in the logics, you never should write this. There exists x belongs to the real numbers. You cannot write this here in this class. Okay? This is calculus. So this is for calculus. In this class, you have to write there exists an x such that x to the real numbers and so on. Okay, so I'm just remember that. So don't make this mistake. Okay. And that's it. Now, the following exercise. So I think we cannot take a break and we just like 5 minutes before we finish, okay? You agree? Yeah. So how do you prefer to discuss the solutions of the home problem sets? In person or I don't know, in Skype, Zoom, or whatever. Because, I mean, I would like to, I don't know, I can't, after every class, every week, we can meet, I don't know, for 1 hour or something with some of you who want to discuss the solutions, okay? But I need you to be at least, I don't know, 3 or something, because just one person is. So don't forget that, okay? Or we can do that also in Zoom, because anyway I have to do that with some guys in Zoom. You wrote the question wrong. It's AX5. The question has plus 19. Okay, maybe I wrote something wrong. Yeah, well, the equation, okay, but it doesn't change anything, okay? So 8. We have the map of a city. And we have here 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. These are going to be streets and avenues. Okay? So we have, where do we have to, so avenues running from the north to the south. So these are avenues, okay? And these are, well, streets. And in some places, we have either a bank or let me check what else. Hotel or restaurants. And that's it, right? And supermarkets. So we have these buildings, I don't know, in the city, in some places here. Let's write. So BS. So we have here in the intersection of the first street and the first avenue, we have a bank and we have a supermarket. Okay? Then we have a supermarket, we have a hotel and a restaurant. We have B R H S H R S R and V. Yeah. So that's the map of the city, and we have some sentences, some statements. Let's write them. And we write. So we have B, H, R, and S, right? And we write, for example, B, I, J means, what does it mean? So IG means that this is the avenue and this is the street. Okay? And now we have to check if the following statements are true and translate them into logical symbolism. So first, there's a hotel on each street where a bank is. So there is a hotel in each street where a bank is. It's a little weird written, but okay. So first of all, we need to define the domain. So we are going to talk about streets and avenues. So the domain is 1, 2, 3, 4, 5, and 6, right? And then we say, so a bank Y and X, right? So this is a bank in the Y avenue and the X street. So how is it written? There is a hotel on each street where a bank is. So where a bank is, so for Yes. Yeah. So wherever there is a bank, okay, in the street, where is a hotel in each street where bank is? So in each street, for all streets where there's a bank, there's a hotel there's a hotel in this street. Okay, so we have here street. So we have a bank in some streets. Yeah? So for all the streets in which there are banks, there are some avenue in which there are a hotel in the streets in which we have banks. Okay? No? So look at this X and this X here. So they are in the same street. Yeah? So in this street where there's a bank, there's also a hotel. Right? Yeah. Is it true or or no? Let's check out. Okay, so in every street where there's a bank, so we have streets. So in this street there's a hotel. In this street there's a hotel. Wait, in every, in this street, so in this street we have a bank, and then we have a hotel, okay? And in this we have a bank, and then we have a hotel, and we don't have banks anymore, so this is true, okay? That there's what? Again, please tell me. Because for this, look, for this street, for each of these streets, there exists an avenue in which there are a bank. Okay. And here's the same. Yeah, here and then for this street that we have from here, there exists an avenue in which there is a hotel in that avenue, but in that street, fixed street from here. Okay. Because these are different. This y and this y are different, okay? The first checked. Now, second. Number B. Let's write that because it's much clearer if you will write it. Yeah. So there's an avenue. So there's an avenue with a bank. There's an avenue with a bank crossing a street. That has neither hotel nor restaurant. A little more complicated. So there is an avenue with a bank. So there's an avenue, one of these, with a bank, in which what happened? Okay, and this, so we have an avenue, and then there's a bank, right? And this is crossing a street, yes, that has neither hotel nor restaurant. So if there's an avenue with a bank, so in this street cannot be neither a hotel nor a restaurant, okay? And then there is an avenue, so there exists, right? So there exists an avenue in which there's a bank. So there's an avenue. Well, we can, but you know, this doesn't. Oh, you mean because you get, okay, yeah, sure. So it's okay. So there's an avenue, y. So let's call it from then. These are streets, and these are avenues, right? So there's an avenue in which there's a bank. And so crossing a street that has neither hotel nor restaurant. The predicate here, B, X, Y. Do we need the predicate what? Sorry, I don't. Yes. No. Because we can write it without that. Okay? And we're going to do that because what does it mean that is crossing? It means that there exists some street in the same. So if we have, this is the street and the avenue, right? And so we say that we have to take this street and say that something happened in this street. So in this street there are no hotel or restaurant, right? So we don't need that. So yeah, there's a bank, and in this street, what happens? So there's so let me write it. It's difficult to just say in words. Hotel with Y and no restaurant with. Okay, here we change this for. No, it's okay. Is it okay? No. So we have here. So for all street, again, there's an avenue with a bank. So we have an avenue and a street. Street avenue, right? You made that complicated. So, and then there exists an avenue. No, there exists a street. Yes, so we have to change here X and X, okay? Oh, wait. Wait. Wait, let me 1 second think about something. X, Y. Wait. I see it. The first one is an avenue. Yeah. So what do we write here? Yeah, Y and X. Sorry. So this is Y and X, right? Now I see it. Okay, so Y and X, and then we have that. I don't know. It was correct, yes. Now it's correct, okay? So, there's an avenue with a bank, and there exists a street such that all the so there's an avenue with this with a bank in the street X, and then in this street X and for all the possible avenues cannot be nor a hotel or a restaurant. Okay? What you mean deposit where? For every street. For every street. No, because we have fixed the street. So we have an avenue. No, yes, we have an avenue. This is an avenue. We have fixed an avenue, and then we say that, no, look, we have an avenue. And then we found the bank, and we fix the street in which the bank is. And then we found, yeah? Street that has the street. Yes, and then we fix that street, and we look for all the avenues in this street, and we say that in this street there is no hotel or restaurant, right? Okay, yeah, I think it's correct. Yes. So, is it true or false? True? Where? So there's an avenue in which there's a bank, right? And here there is no avenue, bank. Well, we have this option or this option, right? And there cannot be hotel or restaurant. So there's a hotel. Here there's a hotel. Where? To what? 4, 2. But we have a hotel here. Yeah. It must be true because, but we have an hotel here, and there cannot be any hotel, right? So this is not true. So this is false. So is it clear why it's false? Look, we have option number 1 and option number 2, and well, option number 3. Here there's a hotel, and here there's a hotel. That's it. Okay. Yeah. So this is false. Okay. And I think it's enough for today. Shouldn't we use implementation? No implementation here for the question there. Okay, that's it. Thank you very much. And please start to resolve your problems. Do not let everything to the end, and that's it.